Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In this module, we learn details about segmentation and paged segmentation. The learning objectives for this module are to understand what segmentation is and how segmentation helps in memory management, to understand how protection is carried out in segmentation, to understand how segments are shared, and to learn how paging is combined with segmentation. So, in the last module, in the earlier module, we learnt what paging is, and we saw how logical address is translated into physical address in the case of paging. In the case of paging, the user's view of memory and actual physical memory are different. The memory management scheme that supports the user's view of memory is called segmentation. So, when you are looking at any program, the user will look at a program as a set of subroutines. There will be a main function, there will be other subroutines, etc., and so on. And the user does not understand or the user does not bother about where the program is placed in the memory. He only looks at the program as a set of data structures, a set of functions, and so on. So, this program is now divided into a collection of segments. So, a segment is looked at as a logical unit such as a main program, procedures, functions, objects, local variables, global variables, symbol tables, arrays, etc., and so on. So, similar to how a user will look at a program, very similarly the program is divided into segments. So, if you look at this diagram, you can see that there is a program or a process, and the program is divided into different parts, or it comprises of a main program, subroutines, it has a stack, a symbol table, and so on. So, this is how a user will look at a program, and very similarly the program or the process is divided into segments. So, each of these units is referred to by a name, or you will have a segment name for each of these units. And you can see here that each of the segments will be of variable length. In the case of paging, when you divided the program into pages, the pages were of equal sized, all the pages were of equal size. But in the case of segmentation, the segments will be of variable size, and the length of the segment is based on the purpose of the segment in the program. So, the logical address space of any process is now a collection of segments, and each segment has got a name and a length. So, the logical address is now a 2 tuple which has got a segment number and an offset. So, let us just look at this figure. The user space has got 4 segments, segment 1, 2, 3 and 4, and the segments are placed in the physical memory. They can be placed anywhere in the physical memory. So, segment 1, 2, 3 and 4 are placed in the physical memory space. So, now we need to remember where each segment is placed in the physical memory. So, in the case of paging also what we did, the program is divided into pages and the pages are placed anywhere in the physical memory, but to remember where the pages are placed in the physical memory, we maintained a table called a page table. Very similarly, here in segmentation, to remember where each segment is placed in the physical memory, a segment table is used. The segment table helps in mapping the user defined addresses to physical addresses. So, what is being held in the segment table? What is stored in the segment table? Each segment table entry has got 2 information. One is the segment base, that is, you put a segment into the physical memory at a particular location, there will be a starting address in the physical memory from where the segment is put in the physical memory. So, the starting address is the starting physical address is what is put in the segment table. So, that is called the segment base. Then you have a segment limit. So, this is the length of the segment. As I told you earlier, each segment has got a different length, or the segments are of variable sized. So, the length of each segment is also stored in the segment table. So, the segment table has got two information, one is the base address of the segment and the other is the length of the segment. So, now let's look at this example. The logical address space has got 5 segments, segment 0, 1, 2, 3 and 4, and these segments can be placed anywhere in the physical memory. So, here you can see that segment 0 is placed in the physical memory starting at memory location 1400, and the length of the segment is 1000, and hence it goes on till the address 2400. Now, this information is stored in the segment table. So, the first entry in the segment table corresponds to segment 0, and the base address is stored as 1400, and the length of the segment, that is 1000, is stored as the limit. And now, we will look at this segment number 1, which is the second segment. It is stored in a place starting from address 6300 and goes on till 6700, which means the length of this segment is 400, and hence in the segment table the starting address of where that segment is kept in the main memory, that is 6300, is added, and also the length of the segment, that is 400, is also added. Very similarly, the segment table is populated for other segments as well. Now, we will see how a logical address is converted into a physical address in the case of segmentation. I told you earlier that a logical address comprises of a segment number and an offset. So, this is the logical address. You have a segment number and you have an offset. So, the segment number is used as an index into the segment table, and you get the corresponding segment table entry. And in the segment table entry, you have the limit value and the base address value. The limit value is compared with the offset that is given in the logical address. So, the logical address has an offset. This offset should be less than the length of the segment. What does this offset mean? What does the offset mean? It means that where within that particular segment the particular memory location is to be used. So, you know the segment number, and within the segment number which is the offset or which is the location which has to be accessed. So, this offset should not be greater than the length of the segment, or it cannot be greater than the length of the segment. If it is greater than the length of the segment, it means you are trying to access a memory location which is outside the limit of that particular segment, and hence you have to check if this offset is less than the limit of the segment. So, only if it is less than the limit of the segment, you carry on to add this offset value with the base address to get the corresponding physical address. If the value of the offset is not less than the limit value, then it is an addressing error, which means this process is trying to access an illegal memory location, and hence a trap is given to the operating system saying that a wrong memory location is trying to be accessed. And to know where the segment table is present in the main memory, you have a segment table base register. So, very similar to how page tables are stored in the main memory, segment tables are also stored in the main memory. But you need to know where the segment table is present, because you've given the segment number from the logical address, you need to look into the segment table to find out the base and the limit. So, the location where the segment table is kept in the main memory is stored in a register called the segment table base register. So, the segment table base register's contents are taken and you access the segment table in the main memory and then try to find the base and limit from within the entry in the segment table. And you also have another register called the segment table length register. What does the length of the segment table refer to? That is, what can you understand by the number of entries that you have in the segment table? Each entry in the segment table corresponds to a segment. So, if you have 10 segments for the particular process, then you will have 10 entries in the segment table. So, if you are trying to access a segment which is greater than this 10, then it means that you are trying to access a segment which is not present in the address space of that particular process. So, you have something called a segment table length register, which will store the number of segments that is used by the program. So, if there are 10 segments in the program, the segment table length register will store a value of 10. And whenever a segment number is generated to look into the segment table, you first check if the segment number is less than the value that is stored in the segment table length register. It should be less than, it can't be greater than the number of segments. So, that is being checked using the STLR or the segment table length register. So, this is how address translation is done in the case of segmentation. So, given a logical address which has a segment number and an offset, you can convert it into a corresponding physical address. And when you have segments, it is possible to have protection. When you look at segments, we saw that, say, a main function is a segment, or data structure is a segment, etc. and so on. So, semantically a similar kind of information will be stored in one particular segment. So, segments will represent a semantically defined portion of the program. So, for example, you can have segments which has got only the text region or which has got only the instructions. You can have another segment which has got only the data region or which has got only the variables, etc. and so on. So, each kind of segment can have different properties. Say, for example, if it is a segment which has got only instructions, then those segments need not be written into. You can just read the segment or you can even execute the segment. So, that particular segment, say a segment that has got only the instructions, can be marked as read only segment or execute only segment. Such a kind of protection can be assigned for those kind of segments. Suppose if you have a segment with data, then you can mark them as read and write and so on. So, depending on the type of the segment, protection can be assigned for the different segments. So, how is this made possible? With each entry in the segment table, you can associate bits for read, write and execute. And depending on the type of the segment, the bits can be assigned appropriately. And whenever a memory mapping needs to be done, memory address that is generated, you just check if the access to that particular segment is as how it is given in the protection bits. Only if it is the same, then access is allowed, else you prevent such a kind of an access. So, thereby you can prevent illegal access to the memory. It is also possible to share segments. How do you share segments? You have two processes, and these two processes, if they want to access the same kind of a program, then those two processes can share the segment. Okay. So, when the entries in the segment tables of two different processes are pointing to the same physical location, then the segment is shared. Say, for example, you can have common subroutines say a function which does a particular function and which can be used by many processes, and such a kind of common subroutines can be shared among the many users. Look at this diagram. You see that there are two processes, P1 and P2, the logical memory of process P1 and process P2. And each of these processes, they use an editor program, and the editor program can have many segments. Here just one segment is shown, segment 0 corresponding to the editor program. So, the editor program is common for both the processes, but they can have their own local data. So, data 1 for process P1 and some other data for process P2. So, while storing in physical memory, the editor program can be stored or will be stored only once, but the data will be stored separately for both the processes P1 and P2. So, process P1 and P2 can now share this segment corresponding to the editor program. So, if you look at the segment table for process P1, you see that corresponding to segment 0, the entry is the same for process P1 as well as for process P2 in the segment table. Only the entry corresponding to data 1 and data 2 for P1 and P2 respectively are different. So, here you avoid storing this editor twice in the physical memory, each time for process P1 and for P2. Rather than that, the editor is stored only once, and process P1 and P2 they share this editor program. The problem with segmentation is that external fragmentation is possible in segmentation. So, here what is done, the segments are of variable sized and they can be placed anywhere in the physical memory. So, you can place them anywhere, and due course of time, like some segments will be put in, will be removed, etc. and so on. At some point in time, you can have many blocks of free memory here and there, but they are scattered around in the physical memory. But if put together, they can accommodate a segment, but because the spaces are scattered around, you are unable to accommodate a segment. So, in this case, the process should wait until more memory is available, or it is possible to do compaction and moving all holes or all free spaces together, so that you can get one big hole and you can put the segment inside. So, how do you avoid this fragmentation? We can look at two extremes. We can think about two extremes. One is to have a full process being considered as a single segment and is being put into a particular place in a particular location continuously. So, this will come down or boil down to a variable size partition kind of memory management scheme. We saw earlier, and this also has got disadvantages. And the other extreme is that you can have each byte as a single segment, and if you have each byte as a single segment, then think of the number of segments that will be possible when the size of the program is large. And when the number of segments becomes very large, the number of entries in the segment table also will correspondingly become large, and the size of the segment table will become very large. So, both the extremes are not that very good. So, it is better to have the average segment size to be small. It should not be very small, it should not be very large, it should be medium enough, so that your external fragmentation is also small. So, another way to reduce this segment size, say if you have a big segment, if you have a function and if you are using that function as a segment, then how do you reduce the size of that function? That may not be possible. So, what is done? You are trying to divide the segment into pieces, or you are dividing the segment into pages. So, similar to how we divided a big single program into pieces called pages, here what is done, a segment is divided into pieces called pages, or you page the segment. So, the next type of memory management scheme that we will learn is the segmentation with paging. So, the example that is being dealt with here is the architecture that has been used in Intel 8386. So, we see that paging has disadvantages, segmentation also has got disadvantages. So, it is better to have a combination of paging and segmentation, so that you can improve on both. So, in this combination or this combining segmentation with paging, the process is first divided into segments, and the segments are in turn divided into pages, so that you avoid external fragmentation. And in this particular architecture in Intel 8386, the maximum number of segments per process is 16 KB. There are 16 KB segments, that is maximum is allowed in this particular architecture. And each of these segments is of size 4 gigabytes. And when the segment is divided into pages, it is divided into pieces of 4 kilobytes each. So, just look at this, just a pictorial representation, which just shows that the blue color thing is the whole process, and it comprises of a number of segments. So, I have just shown segment 1, segment 2 and etc. You can have so many such segments, you can have 16 kilobyte segments. So, S1, S2, S3 etc. up to S16 kilobyte. So, so many segments are allowed, and each of these segments can have a maximum size of 4 gigabyte. And when you are dividing this segment into pages, each of the 4 gigabyte is the maximum size allowed for each segment, and the segment can be divided into pages, and the size of each page is 4 kilobytes. So, now the logical address space is divided into 2 partitions. Totally you can have 16 kilobyte segments, but now the segments itself they are categorized into 2 categories. One is the segments that are private to the process, and the other is the segments that are shared among all the processes. So, the logical address space, the 16 kilobyte segments are divided into 2 categories. You can have 8 kilobytes of private segments and another 8 kilobytes of shared segments. And the information about these segments are present in descriptor tables. Earlier when we learnt about segmentation, we understood that a process is divided into segments and information about the segments are placed in a segment table. But here in this case, the information about the segments are placed in something called a descriptor table. The descriptor table is very similar to the segment table. Because you have got 2 types of segments, that is the private segments and the shared segments, you have 2 different descriptor tables for each type of segments. So, the first type, the private segments information is placed in the local descriptor table, and the second partition, that is the shared segments information, is placed in the global descriptor table. And each entry in this local descriptor table and global descriptor table consists of 8 bytes. Similar to how you will have information in a segment table, here also in the LDT and the GDT, you have information about the base address of the segment and the length of the segment. So, the LDT and GDT are very similar to segment tables. So, just I have shown pictorially shown what you have in LDT and GDT. The entries, each of the entries correspond to each segment that is present. So, in LDT you can have a maximum of 8 kilobyte entries corresponding to the 8 KB segments that are available. In GDT you have 8 kilobyte entries corresponding to the 8 kilobyte segments that are available. So, each entry has got the base address of the segment and the limit of the segment. So, the logical address is a pair, it is comprises of a selector and an offset. So, the selector is a 16-bit number which is again divided into 3. There is 13 bits segment number, 1 bit for this G and 2 bits for P, which is the protection bits. This G value decides whether the LDT should be used or the GDT should be used, and this segment number is used as an indexed into the LDT or to the GDT depending on what value is being stored here. So, S is the segment number, G indicates whether GDT or LDT, and P indicates protection bits. So, offset is a 32-bit number which shows the location of the word within the segment. So, this selector and an offset correspond to the segment number and an offset that you had in the earlier segmentation case. So, this 13-bit segment number is used to identify one of the 8 kilobyte segments, that is one of the 2 power 13 entries in the descriptor table. So, the base and the limit information about each segment is kept in the descriptor table, and this is used to generate a linear address now. So, now what is done? You have a limit in the segment table entry or the descriptor table. That limit is now first checked for validity. If it is not valid, a trap is given to the operating system. If the limit is valid, then the offset that you have in the logical address is added to the base address in this descriptor table to get the 32-bit linear address. And the linear address is now translated into a physical address. Now, each segment is divided into pages. So, now you can see that you have S1, S2, etc. up to 16 kilobyte. This is the set of segments, and each of the segment is can be divided into pages, and you have a GDT corresponding to the different segments that you have, the segment table or the GDT corresponding to the segments, and each segment is also divided into pages. So, when you are dividing each segment which is of size 4 gigabyte into pieces of size 4 kilobyte, you get 2 power 20 such pages for each segment. When you have 2 power 20 pages for each segment, then you need to have a page table. So, how many entries will be there in the page table? Corresponding to each page, you need to have a page table, and hence you will have 2 power 20 entries in the page table. And each entry in the page table consists of 4 bytes, and the size of the page table hence becomes 4 into 2 power 20, that is 2 power 22, which again is very large, and hence the page table is also paged, or the page table is also divided into pages. So, now to identify each page of the page table, now an outer page table is needed, and this is called a page directory. So, now the 32-bit linear address is divided as a page number and an offset. The page number is again split into 2, 10, 10, and offset is 12. Why 12? Because the page size is 4 kilobytes, 4 KB is 2 power 12, and hence 12 bits for the offset. Remaining 20 will go to the page number. Now, again the page table is also broken into pages, hence you have 2 entries 10 and 10. So, now I have just shown that the page table for the segment is also now divided into pieces. So, you have one pink piece and green piece, shows that different pieces of the page table are available, and hence to identify each of these pages of the page table, you have another outer page directory, and you have entries corresponding to each of the page in this page directory. So, now this shows Intel's address translation. Now, combining together whatever I have told you till now, the logical address is divided into selector and an offset, and the selector is used as an index into the descriptor table, and you get the base address and the limit. The base address is combined with the offset to get a linear address. The linear address you have, as we have seen, you divide it into 10, 10 and 12 bits. So, for the directory 10 bits. So, this 10 bits is used as an index into this page directory, and from there you get an entry which is used to identify the page table. The second 10 bits is used as an index into this page table. You get the page table entry, you add it with the offset to get the corresponding physical address. So, here we have seen that you have combined paging with segmentation, and thereby you avoid external fragmentation, and you can also reduce little of internal fragmentation. So, summarizing what we have learnt in this module, we saw that a process is divided into segments in the case of segmentation, and the logical address comprises of a segment number and an offset. The segment number and the offset is converted into a physical address using proper address translation mechanism. And the problem with segmentation is that you have external fragmentation, and hence to avoid external fragmentation and to bring in the good features of paging, you combine paging with segmentation. So, in architecture Intel 8386, we saw how paging is combined with segmentation. The references, acknowledgement. Thank you.